In the last test your understanding, we said Fg equals gm, mass of the moon, times mass of the Earth, divided by the distance between them squared. And then this part says, on which object is this force applied? This same force is applied on the Earth and the moon, because if we have the Earth exerting a gravitational force on the moon, then the moon has to be exerting an equal magnitude, same type, and opposite direction force on the Earth. So while the Earth is pulling the moon inwards, the moon is pulling the Earth outwards. Which object has a greater acceleration? We know that acceleration equals force over mass. So we're trying to figure out which one has a greater acceleration. The forces are the same, so what's happening to the mass? One, we have a very tiny mass, and when we have a very tiny mass, that means we have a much larger acceleration. That's the moon, acceleration of the moon. Meanwhile, the Earth's mass is much larger with the same size force, so our acceleration becomes much smaller. Acceleration and mass are inversely related. Now we have planet X and Y exerting a gravitational force on each other. Determine the gravitational force, F prime, of each of the following cases. For these types of problems, and they're so common, start with your equation and then figure out what is happening. So we have mass of X and mass of Y. For this instance, we are doubling the mass of X. So we could write a 2 there, but I don't like to put a 2 there because that can get kind of messy and confusing and we might forget something. So I'm going to write it off to the side. So I know I'm multiplying my numerator by 2. Not doing anything to my denominator. Well, if I'm multiplying by 2 on the right side of the equation, I have to do the same exact thing over here, so my force is doubled. Mass of Y is doubled. That's the same exact thing because the commutative property of multiplication tells us that no matter where I put that 2, if I put it here or if I put it over here, it's the same exact result. The mass of both X and Y are doubled. So now we've got mass of X, mass of Y over R squared. So now there's a 2 here and a 2 here. 2 times 2 is I'm multiplying by 4. So I'm multiplying the right side of the equation by 4. I've got to multiply the left side of the equation by 4. Our force is quadrupled. The distance between them is doubled. GMM over R squared. So again, it's kind of like I'm writing in a 2 there, but I don't like to do that. Remember that whatever you're doing to your radius, we are squaring that. So 2 squared is 4. So I'm multiplying the right side of the equation by 1 over 4. I'm going to multiply the left side of the equation by 1 over 4. So I get gravity is reduced by 4. The distance is 1/3 as much. With all of this, I'm assuming there's a constant mass. So when I plug in 1/3 to this equation, it gets squared. So that means I'm multiplying the right side by 1/9. So I'm multiplying the left side by 1/9. My force is reduced by 1/9. If both masses are doubled and the distance between them is tripled, GMM over R squared, so both of them are doubled, so 2 times 2 gives me 4, divided by 3 tripled is 27. So I'm multiplying the right side by 4 over 27. I need to multiply the left side by 4 over 27. Whatever that gives you. What's the equation that gives gravitational field strength on the surface of a planet of mass m and radius r? Show how this equation is derived from 2 equations for the force of gravity. All right, so we know the acceleration for any system is equal to the net force divided by the mass. If the only force acting is the force of gravity, then our acceleration equals g times m over r squared divided by m. One of these m's cancel out, and what we have solved for is our acceleration due to gravity. So g equals big G times m over r squared.